Okay, well, good morning, everyone. Again, I'm sorry for the short notice. Something came up family-wise with my intended schedule, as I joked it might. So I'm going to try and fit a couple of these videos in today. So we're looking at the second and the third video. I don't know if anyone will join us because I know it was incredibly short notice. If anyone does join, though, if you could please let me know whether you can hear me, that would be great. It's always good to know you're not talking in vain. Okay, so I think the topic that we agreed upon for this conference was predicting the charge on ions and that type of thing. Okay, so it would be great if you had a periodic table in front of you as you would in a typical exam. So I'm going to go grab mine real quick. Okay, so I'm a chemist with a periodic table, so I'm pretty dangerous right now, in a good way. Okay, so we want to look at the periodic table, and we can see that the periodic table consists of geometrical shapes. So I'm just looking at the video, making sure I can see it, because if I can't see it, I don't know if you'll be able to see it. This is an overview of the periodic table. Pardon my big head. Okay, I think you can see it. Okay. And it's a block arrangement. We have the F block, the S block, the D block, the P block. So there's 4 blocks. And then we have the members that don't really belong anywhere. We have a hydrogen atom and a helium atom. So they're kind of odd. They don't really belong. So these are all blocks. Now, the good news is we don't really have to worry about the F block in Chem 65. So we can pretty much ignore the F block in Chem 65. That's something that you would look at in Chem 101. So we can ignore the F block. Okay. So we'll ignore the F block. And then we notice, and actually, we can pretty much, although we don't ignore the D block, for predicting charge, we'll ignore the D block. So we do look at the D block in Chem 65, but you can't really predict the charge of the D block, so for that reason we ignore it. Okay. So we're going to ignore the D block also. So what's left are just the S and the P blocks. Now, if you look at groups, so the groups in the S block, well, that's groups 1 and 2. And then we've ignored the D block, that was groups 3 through 12. And then we have our first group, which is group 13, and it goes through group 18. So there's 1, 2, and then 13 through 18. So there are 8 groups total. There are 8 groups total. If ever you hear somebody talking about the octet rule or the rule of 8, they're talking about the groups, the 8 groups in the S block and the P block. So that's where the idea of the octet comes from. Okay. The P block is special in that approximately 50% of it is nonmetals and about 50% of it are metals. So the nice thing, we'll ignore hydrogen and helium for now because they They don't represent what we're going to talk about. Let's ignore hydrogen and helium. See if anyone's managed to join us. No, that's okay. I announced it pretty late. We notice that the S block are all metals. The S block, let's see if you can see that. Odd because I'm looking at my head. The S block are all metals. And the P block, let's shade the metals without shading. So the parts of the P block that I've shaded here are nonmetals. Now, the way metals and nonmetals behave is different. Metals are weak, and so they lose valence electrons. What's a valence electron? A valence electron is an electron that's on the outer surface of an atom. So think of an apple as an analogy. The skin of the apple would be the valence shell of the apple. The flesh inside the apple would be the core of the apple. So we're interested in chemistry predominantly on what's on the outside of the atom, because that's what's going to interact with another atom during a chemical exchange. So metals are weak. They tend to lose what they have. They lose their valence electrons. Nonmetals are strong, on the other hand. They tend to gain valence electrons. Up to 8. So they tend not to go over 8. So for example, if you have 5 valence electrons, you would gain an extra 3. If you have 6 valence electrons, you would gain an extra 2. If you have 8 valence electrons, you would gain 0. Okay, so this is very important. Knowing what the type of element will do, and knowing where these types of elements are found in the periodic table. Okay, so I'm going to have to erase this in a second. So you'll be able to pause this if you need to. But I don't want to pause it because we have a lot to get through in this hour. Okay, I'm going to erase this now, or at least some of it. So let's look at the S block. S block only contains metals. So you can have, actually, I need to put groups back in, don't I? We've got groups 1 and 2. Let's look at the charge that can be formed for group 1 metals. The group tells you how many valence electrons you have. So if you're in group 1, that means you have 1 valence electron. So look at all the elements in group 1. You've got lithium, sodium going down group 1, lithium, sodium, potassium, rubidium, cesium, francium. They all have 1 valence electron. They're metals, so they lose the valence electron, and the electron has a negative charge. If you lose something with 1 negative charge, you are left with 1 positive charge. So everything in group 1 will form a +1 charge. In group 2, you have 2 valence electrons. So if you look at beryllium, magnesium, calcium, strontium, barium, radium, you'll lose 2 valence electrons and you'll be left with a +2 charge. So typically, if it's just a plus charge, 1 plus charge, you don't write the number 1, you just write the plus. And if it's a +2 charge, you would represent the number 2. That's easy. Anything in the S block can be predicted. If it's in group 1, it forms +1. If it's in group 2, it forms +2. Let's have a look at group 13. Now, group 13, we treat this as the third group. Even though it's group 13, we're ignoring the 10 D groups. So 10 from this 13 gives us 3. Let's look at aluminum. So aluminum is found over here. It will be our representative member of group 13. We know aluminum is a metal. It's below this line in the P block. Aluminum, because it's in group 13, will have 3 valence electrons. So over here for the metals in the P block, you would just subtract 10 from the group number, where again 10 represents the D groups. So 13 minus 10 is 3. Aluminum has 3 valence electrons. It's a metal, so it loses them, and it forms a +3 charge. Okay. So we are predicting, for example, sodium would form a plus charge. We have calcium that will form 2 plus charges. And aluminum will form 3 plus charges. And we can do this for anything in the S or the P groups. Okay, so that's the metals. What about the nonmetals? We know that nonmetals are strong. They tend to gain valence electrons until they have a total of 8. So a quick way to look at this is look at group 18, the lastmost group. Again, you would subtract 10, 10 representing the D groups. So 18 minus 10 is 8. So anything in group 18 already has 8 valence electrons. So anything in group 18 doesn't want to lose or gain valence electrons. Well, if you don't want to lose or gain electrons, we would expect your chemistry to be limited if existent. So anything in group 18, noble gases tend to have limited to 0 chemistry. They have everything they already need. So let's have a look at something more useful. Let's look at something in group 17. So 18, let's say, would form 0 charge. Let's look at group 17. Group 17 means it has 7 valence electrons. So you want to gain electrons till you have 8 total. So if you already have 7 and you gain an extra electron, you're going to have 1 negative charge. So for example, chlorine, when it accepts a negative charge, would only accept 1 to form chloride. On the other hand, if we look at group 15, so 15 minus 10 is 5. So nitrogen, for example, no space here, this would form a -3 charge. Nitrogen has 5 valence electrons. It would like 8, so it's going to accept an extra 3 valence electrons. We could have nitrogen 3 negative. Again, I'm assuming everyone's in class, and I don't see anyone else joining us. If you do join us, can you go ahead and send a message on the chat so I know that the volume is okay? Because right now I have no way of knowing if you can see this. Okay, so I'm going to erase the board and we'll start looking at some examples. Okay, so here I'm interested in predicting charge and using that to make chemicals. So for example, what if we had, I'll do it down here, what if we have lithium and fluorine? We have lithium and fluorine. We identify which groups of the periodic table lithium and fluorine are from. We notice that lithium is from group 1. It's a metal, So it's going to form one charge. We have lithium plus. Fluorine, we identify from group 17. It's a halogen or a halogen. It's in group 17. 17 minus 10 is 7. It has 7 valence electrons. Fluorine is also a nonmetal, so it's going to gain 1 extra electron because it wants 8 total. The lithium forms a plus charge. Fluorine forms a negative charge. They come together because opposite charges attract. So a plus charge is attracted to a negative charge. And we typically always write the plus charge first. So here they're separate, here they're together. They're held together by electrostatic forces between the charges. And we notice that the whole thing is neutral. So a plus charge plus a single negative charge is 0. So these species must be neutral. That's one way that you can verify that you've done it correctly. You must cancel all charges by an equal number of opposite charge. So I've predicted that this compound, LiF, comes together in a 1-to-1 ratio. So we would say LiF, we have a 1-to-1 ratio. Remember, the ratio is moles. This is a 1-to-1 mole ratio. So if you're going to make this, you would have a mole of lithium, a mole of fluorine. And what would the chemical be called? This would be called lithium fluoride. Let's inspect the name of this chemical. You'll notice that the chemical, the first element is always the metal, the second element is always the nonmetal. This is just because on the left of the periodic table we have the metals, so on the left of the structure we have the metal also. You'll notice that the name of the element, lithium, and the name of its charge are exactly the same. So lithium with no charge and lithium with a plus charge are both lithium. However, they are different. One of them has lost an electron. So the positive charge, we call this a cation. So a metal that's lost a valence electron and has now acquired a positive charge is called a cation. So strictly speaking, this is the lithium cation. The nonmetal has a different name than the anion. So a negative charge, we call this an anion. Nonmetals gain valence electrons and form anions. The element is called fluorine, but the anion is called fluoride. So we have a different ending that signifies that this is not just a mixture of lithium and fluorine. This is something different. This is a new form of matter that's come together because lithium and fluorine reacted in a 1-to-1 mole ratio. Okay, so that's a straightforward example. I'm going to erase the board and we'll look at another example. What about lithium plus oxygen? We know that lithium has a plus charge for reasons stated earlier. Now, oxygen we identify as a nonmetal. We can see oxygen is located in group 16. So 16 minus the 10D groups is 6. So we know oxygen has 6 valence electrons. It's a nonmetal, so it's going to gain more until it has 8 total. It has 6, it wants 8, it's going to gain 2 more. That's going to form 2 negative charges. Now, when I add these together, it won't give me 0, and that's a problem. It has to give me 0. So this just tells me that I need 2 lithiums. 2 single plus charges plus 1 single negative 2 charge is going to give me 0. So now I know that this forms a 2-to-1 mole ratio. Once again, the material is neutral overall because the sum of all the cationic charges equals and cancels the sum of all the anionic charges. So lithium forms a 1-to-1 mole ratio with fluorine. Lithium exists in a 2-to-1 mole ratio with oxygen. This chemical is called lithium oxide. Again, it's a mixture of lithium and oxygen, but lithium oxide is not just lithium and oxygen. It's lithium and oxygen that have exchanged electrons between themselves. So the 2 electrons gained by the nonmetal are actually coming from the metal. So the nonmetal cannibalizes the metal. That's another reason, well, that's the reason why the charge must be 0. Because it's really one event looked at in 2 different ways. So instead of lithium oxygen, we have this suffix ending again, IDE. Notice, however, there's no prefixes. Notice we don't say dilithium or lithium-2. It's just lithium oxide. Why is that just lithium oxide? Well, it's assumed that the chemist knows, based on the location of the material in the periodic table, he or she could recreate the charge. There is no need to baby the chemist. So naming chemicals is a very efficient process. All the information given a periodic table to look at is all locked in there. You find the location, you predict the charge, you reacquire the 2-to-1 mole ratio. I'm going to erase the board and look at a couple more examples. Lithium and nitrogen. Lithium has a plus charge. Nitrogen, if you look at the periodic table, is in group 15. 15 minus the 10 D groups is group 5. So nitrogen, which is a nonmetal, has 5 valence electrons. As a nonmetal, it wants to gain up to 8. So it already has 5, so it wants to acquire 3 more. That's going to be 3 negative charges. A positive charge won't cancel 3 negatives, so I need to multiply this by 3. At this stage, it's important to point out that we cannot simply put a 3 here. We cannot simply put a 3 here because lithium doesn't have 3 valence electrons. It only has 1. But you can have 3 of them. So we can't change the superscript, but we can change the coefficient. So 3 single positives will cancel out 1 negative 3. When we write the final product, the coefficient that we had as a reactant now becomes a subscript because it's a part of something new. Subscripts apply to what's immediately before them. I couldn't, for example, just do this. If I wrote that, that would mean I've got 1 lithium and 1 nitrogen, or I've got 3 of everything. So that would be totally wrong. That's the only place that subscript can go. It means I have 3 lithium for every nitrogen. This is called lithium nitride. Again, the cation keeps the name of the element. The anion has the prefix of the element, but then the suffix is changed to IDE. Lithium nitride. Again, there's no hint of a prefix anywhere. So anytime you mix an S block metal with a nonmetal, you would name it this way with no prefixes. Incidentally, when we do mix a metal plus a nonmetal, we're making an ionic compound. Ionic compounds, the vast majority of them, are a mixture of metals and nonmetals. Okay, I'm going to erase the board. Really hope you can hear this. Okay, so I think we've used lithium enough. How about we have something other than lithium? What about magnesium and chlorine? Magnesium is in group 2 of the periodic table, so it's going to form a +2 charge. Chlorine is in the same group as fluorine, and we already know that that formed a negative charge. So +2 and a single negative, so clearly I need a multiple of 2 here. And that coefficient multiple here will become a subscript over here. So I'm predicting a 1:2 mole ratio. Again, the sum of the charges must cancel. Sum to 0. We just call this magnesium chloride. Again, the cation takes the same name as the element. The anion has this suffix IDE. So chlorine becomes chloride. How about magnesium with, we already saw nitrogen in the lab. Let's see magnesium with, oh, we saw oxygen too. Let's try oxygen anyway. Magnesium and oxygen, magnesium forms a +2 charge. The charges never change for the S block. If it's +2 once, it's always +2. Oxygen we saw forms a -2 charge. Now here they're the same number, so when we add them, they'll cancel. Here it's just a 1:1 mole ratio. And this is just called magnesium oxide. So we are indeed using the location of the elements in the periodic table to predict the mole ratio that they'll form when they form ionic compounds. This is something you'll have to do on your Gibbs exam. Okay, I'm going to double check the topics. I wrote the topics down, so I want to make sure that I'm covering everything that we said we would. Double checking what we did say we'd cover. Predicting charge of ions, predicting formulas and nomenclature. Yeah. All right, so we're definitely doing everything we said. Let's look now. So everything so far has been monatomic. So what does monatomic mean? Oh, and I can see Deirdre has just joined us. Deirdre, if you can hear me, can you just send a quick message saying, like, can hear you or something? Please, that'd be great. Okay. So far, we've looked at monatomic ions. I can hear you. Okay, thanks very much. So far, we've looked at monatomic ions. So what's a monatomic ion? These are, well, ions of only one element. So for example, chloride is one element with a charge. Sodium plus is one element with a charge. Everything so far, there've been a multiple of charges, but it's only been one element housing that charge. But we next need to look at polyatomic ions. So polyatomic ions are ions consistent of many atoms. So polyatomic ions. So polyatomic means many atoms, e.g., so here you've got 4 atoms, a carbon and 3 oxygens, and the whole thing has a -2 charge. We could have NH4 plus. That's 5 atoms, 1 nitrogen, 4 hydrogen, and the whole thing has a positive charge. I need you to learn, if you either look at the Tro book or the OpenStax book, or if you just Google polyatomic ions, generic tables will come up. I would ask you to become familiar with whatever you find. You'll typically, wherever you look for polyatomic ions, you'll get a similar list. Become familiar with that list. In fact, know that list by heart. Typically at Chem 65, that's something you would have to do, is be able to recite some polyatomic ions, because it's only when you know them, you know the charge. So you can't use the periodic table here. You have to learn them by heart and then use them to predict a ratio. So I'd ask you to do that. So let's look at some examples. So what about lithium and carbonate? So lithium, we know from earlier on, it has a plus charge. Carbonate is something that you would memorize as a polyatomic anion, has 2 negative charges. So I need 2 here to scale up this plus charge to cancel that one. So again, I would have a 2 to 1 mole ratio. And this is called lithium carbonate. So again, the cation has the same name as the element. The anion, this polyatomic anion, you would just have to learn. Typically, an anion that ends with 8. So 8 implies oxygen, so it contains oxygen. A carbon obviously implies that it's a mixture of carbon and oxygen. So whenever you see this prefix 8, it typically means oxygen. What about, Deirdre, if you have a question, you can text it in the chat box. What about, What about aluminum and carbonate? So aluminum, we know, is in group 13. It's a metal. 13 minus the 10 d groups is 3. The metal, it's going to lose its 3 valence electrons. So it's going to form 3 plus charges. I've got to somehow add 3 and 2 together to make 0. So here's where you just use, you'd factor them out. So you look for a number that 3 and 2 will factor into. So clearly 3 and 2 will factor into 6. And to make 3 go into 6, you'd have to multiply it by 2. To make 2 go into 6, you'd have to multiply it by 3. Try not to break my neck on the cable. So this would be Al2. The coefficient becomes a subscript now. Now I've multiplied my polyatomic ion. Whenever you multiply a polyatomic ion, you have to put the whole thing in parentheses. So again, if you just have a multiple of 1 polyatomic ion, no parentheses. But if you have 2 or more polyatomic ions, you have to put the whole thing in parentheses. If you don't, if I were to remove the parentheses, it would read 33 oxygens rather than 3 multiplied by 3 oxygens. Okay, so that's a crucial point. This is clearly a 2 to 3 mole ratio. And the name of this chemical is aluminum carbonate. Notice there are absolutely no prefixes. It's not dialuminum tricarbonate, for example. That's completely incorrect. Why are there no prefixes? Because everything we've used so far has a charge that won't change. It's predictable. And if it's predictable, you can figure out how many there are. You can figure out the mole ratio. So there's no need to have a prefix. Okay. Again, if anyone has a question, I'll stop if I hear a chat ping. Otherwise, I'll just carry on. Okay, so I'm going to erase the board and I'll erase the board. Instead of looking at ionic compounds, actually, we'll do a couple more polyatomic ions, and then we'll spend a few minutes looking at some covalent compounds. What about ammonium and phosphate? So these are 2 polyatomic ions that you would find in a generic table of polyatomic ions, and I'd expect that you'd know these as a Chem 65 student. So you just have these are what you would just memorize. So I have a plus charge and a negative 3, so I need a multiple 3 here. We're multiplying a polyatomic ion, so I need parentheses. I've got NH4 in parentheses 3 times. So that coefficient 3 is that subscript 3. Parenthetical because of its nature as a polyatomic ion. I only have 1 phosphate, so no need to put that in parentheses. This is a 3 to 1 mole ratio. The name of this chemical is ammonium phosphate. Not triammonium phosphate. Again, there's no need for any prefixes because the charges, that's always going to be plus, negative 3. That's always going to be plus 1. And that's always going to be ammonium phosphate. Okay, maybe one or two, or probably one final one just to get us going. And if, if the class feels like this is a subject they need a bit more help with, we can always do an extra conference. But this is just meant to supplement what's already available with the other materials. So, okay. What if you have a choice? What if you can't predict the charge? Lead, for example, is something that you can't predict the charge of because it can adopt more than one type of charge. It's a metal, it's in the P block, but P block metals are typically able to acquire more than one type of charge. They're very different than S block metals. So you can commonly find lead with 2+ charges, and you can also commonly find lead with 4+ charges. So this is going to affect the mole ratio of the ionic compound that we produce. So here we have a 2 and a 3. That's going to factor into 6. To make 2 go to 6, you multiply it by 3. To make 3 go to 6, you multiply by 2. Here I have a 4 and a 3. 4 and a 3 is going to factor into 12. To make 4 go to 12, you multiply it by 3. To make 3 go to 12, you multiply it by 4. So lead, it has 2 letters, but it's one element, so there's no need for parentheses. So that's just Pb subscript 3, single element, it's monatomic. But phosphate is polyatomic, so I do need parentheses. I have my 3 to 2 mole ratio. Here I have lead again, 3 of them. So here I have 4 phosphates. So here I have the same ingredients, but in a different mole ratio. This is a 3 to 4 mole ratio. So now we have a naming problem. I can't just call these lead phosphate because they're different. They both contain lead, they both contain phosphate, but now there's a need for additional nomenclature. So typically when this happens, we use what's called stock notation. So these are Roman numerals. So you're expected in Chem 65 to know the Roman numerals 1 through 10. The Roman numerals are given to represent the charge on the original cation. So the original cation here was 2. So we would call this lead Roman numeral 2 phosphate. Again, we use stock notation. It's a Roman numeral, and it reflects the charge on the original cation. The charge on this cation is 4, so this would be lead 4 phosphate. Again, the name now is more complex because we had a choice, we had to distinguish between 2 options. Somebody looking at this name is now able to recreate the structure. I know that there's a lead with a 4+ charge, and it's next to a phosphate with a -3. Oh, it must be in a 3 to 4 mole ratio. Versus, I know I have lead with a 2+ charge, next to a phosphate with a -3 charge, oh, it must be in a 3:2 mole ratio. So we use stock notation whenever the cation can acquire more than one type of charge. Okay. So we have about 10 minutes left in this, and then we'll take maybe a couple of minute break, and then I have the second conference as close to 12 o'clock as possible, maybe 12:05. Give everyone a chance to stretch the legs, myself included. Okay, so I'm going to erase the board, and I'd like to look at just a few examples of compounds that are exclusively nonmetals. Actually, strike that. If anything, I'll make an extra video. I think for now, let's just stick. Yeah, for now, let's just stick with ionic compounds. I don't see the need to change it right now. Let's just stick with ionic compounds. How about, let's see if I can get some examples. Yeah. What about K plus NO3 minus? Potassium is in group 1. It forms a plus charge. Nitrate is a polyatomic ion that you would memorize. Clearly, this is a 1-to-1 ratio. There's only one nitrate, so there's no need for parentheses. So we would just call this potassium nitrate. What about if we had NO2? So we've got one less oxygen. Now, whenever you know what the 8 is, so I know this is nitrate, I've memorized that. If ever you have one less oxygen, the ATE suffix becomes ITE. So this would be potassium nitrite. So in a 1-to-1 mole ratio, but now we have potassium nitrite. So again, 8 minus an oxygen typically gives ite. So you might recognize the name nitrite. This is the chemical, or one of the chemicals they use to cure lunch meat. So if you're pregnant, your physician will tell you not to eat cold cut meat. It's not the meat, it's the nitrite. So you can go to a nice delicatessen and you can get nice meat that has no nitrites. That's fine. Nitrite. Let's look at a couple more examples. So this is important. 8 minus an oxygen is ite. So let's look at sulfate and sulfite. Now, sulfite is the chemical, typically on a bottle of wine, it will warn you contains sulfites. So let's have a look at ammonium. Let's look at sulfate. And then we'll look at ammonium. So 8 is 4, minus 1 is 3. You don't change the charge though. So this will be ammonium sulfite. This is the stuff in wine that's not ideal for you. Okay, we have a 1 and a 2, so I need a multiple of 2 here. 2 positive charges will cancel the 1 single -2 charge. I have a multiple of polyatomic ions, so I'll have to use parentheses. This is ammonium sulfate, a 2-to-1 mole ratio. We have ammonium sulfite. We've got this 8 to 8 suffix change because I've got one less oxygen. Still in a 2-to-1 mole ratio though. It's vital that you can do this in Chem 65 because as you can see, the mole ratio will affect the mole mass. So when you do mole calculations, if you think back to the mole video, one of the things you have to be able to do is to calculate the weight of this thing. So it depends on how many elements you have. Well, how many elements you have depends on the mole ratio that you predict. So if you make an error predicting the mole ratio of elements in an ionic compound, you'll calculate an incorrect weight of a compound, and then all of your calculations will be wrong. It's vital that this is something that we can do. And it's vital that we can do it now because it will be as soon as you can do it in Chem 101. Can't really think of anything else. So this is obviously not an exhaustive anthology of the material, but this is enough to show proof of concept so that you can then go pursue extra examples. In addition to the material that's available online and in your textbook, etc., go to Google and you can just go to a search engine and type in either nomenclature practice or mole rate, predicting mole ratio practice, and you'll get a billion gajillion worksheets with answers that you can self-test. And allow me 20 issues. While I think on, I've updated the course site because I realized that we actually don't meet on Thursday. The school is closed for Cesar Chavez Day. So in lieu of that, I've made sure I updated the Canvas page. So you actually have a workshop to do on this content and content that's going to be in the next video. Balancing equations, looking at molecular ionic and net ionic equations. So that will be excellent practice for you. So if there are any questions, please ask now. Otherwise, I'll close this down in about a minute, and then we'll start the next video. I'm thinking maybe around 5 past 11, sorry, 5 past 12, or just a few minutes later than scheduled. Okay, so here are no questions. I'm going to close up, and I'll see you if you're here in about 8 minutes.